As per the current problem, we need to match the systems in list 1 with characterizations in list 2. The systems given in list 1 are y of t is equal to log of 1 plus mod xt and y of n is equal to x of n into x of n minus 2 plus 2. Y of t is equal to 3 into x of t minus 4, and the characterizations given are in the list to nonlinear, causal and stable, memoryless, invertible and time variant, nonlinear, time invariant and memoryless. So now let us pick the system in A, that is y of t is equal to log of 1 plus mod xt. We see that this doesn't satisfy superposition principle, so the system is nonlinear. Also, we see that here the delayed version of input would give delayed version of output, so the system is time invariant. Here, the output at any instant depends on the input at that instant, so the system is memoryless and hence causal. Also, we see that for a bounded input, the output is bounded, so the system is stable. So, from this, we see that A can be mapped to 3. Now, let us pick the system in B, that is y of n is equal to x of n into x of n minus 2 plus 2. Here, also we see that the system is actually nonlinear as it doesn't satisfy superposition principle. Here, the delayed version of input would give delayed version of output, so the system is time invariant. Here we see that the output at any instant depends on current or past inputs, so the system has memory but causal. Also, here for any bounded input, we get bounded output, so the system is stable. From this, we can see that B can be mapped to 1. Now, let us pick the option C, in which the system is given as y of t is equal to 3 into x of t minus 4. Here, we see that the system is nonlinear as it doesn't satisfy superposition principle. It is time invariant, and also here the input at any instant, sorry, the output at any instant depends on the current input, so it is memoryless, causal, as bounded input at any point of time would give bounded output, so we see that the system is stable. And finally we see that in this case the input can be the system is invertible, as the output from the output at any instant the input can be recovered using the inverse system x of t is equal to y of t plus 4 divided by 3. So using the inverse system written, we can recover the input back. From this we see that the system is invertible. Also please note that the systems in option A is non-invertible because of the absolute the mod operation present. So from this we see that C can be mapped to 2, and also we see that the system in option B is non-invertible, as the output y of n cannot be recovered sometimes whenever the input is 0 or x of n minus 2 is 0. So from this the correct mapping is A should be mapped to 2, B should be mapped to 1 and C should be mapped to 2. From this we can get the mapping of the systems in list 1 with the characterizations in list 2. Now let us consider another problem in which there is a discrete time signal x of n given. There are two statements given as related to x of n. The statement one is if x of n is conjugate skew symmetric, then x of 0 is equal to 0. Then second statement is if x of n is conjugate symmetric, then x of 0 must be real. We have to pick the correct option. We have to pick which of these statements are correct. Let us consider the first statement, as per which x of n is conjugate skew symmetric. So it must satisfy x of n is equal to minus x star of minus n. Now, if we substitute n is equal to 0 here, we see that x of 0 is equal to minus x star of 0. So, from this, we see that x of 0 is 0 or purely imaginary. Then we see that the statement 1 is not correct. Now, as per the statement 2, we see that x of n is conjugate symmetric. So, x of n is equal to x star of minus n. So if we substitute n is equal to 0 here, we get that x of 0 is equal to x star of 0. From this we see that x of 0 is purely real, that is x of 0 belongs to R. So the statement 2 is correct. So from this we see that for any given discrete time signal, if x of n is conjugate skew symmetric, x of 0 can be 0 or purely imaginary. If x of n is conjugate symmetric, x of 0 must be real. So from this, we see that only the statement 2 is correct. There is a signal x of t which is given as shown in the figure. For t greater than or equal to 0, x of t is 1, and for t less than or equal to 0, x of t is minus 1. We have to find the even and odd parts of the signal x of t in terms of the unit step function u of t. We know that the given signal x of t can be written as u of t minus u of minus t. From this, we see that the conjugate symmetric or even part of the real signal given can be written as x of t plus x of minus t divided by 2, which can be written as u of t minus u of minus t plus u of minus t minus u of t divided by 2, which is equal to 0. Similarly, the odd part of the signal xo of t can be written as x of t minus x of minus t divided by 2, which on simplification can be written as u of t minus u of minus t. From this, we see that the given signal is conjugate skew symmetric or odd, because of which even part of the signal is 0 and odd part of the signal is the signal itself. Now, let us consider another problem, as per which there are two signals x of t and y of t which are given as shown. That is, x of t is 1 in the range 1 to 2 seconds, and y of t is 1 in the range minus 4 to minus 2 seconds. So here we say that y of t is a derived version of x of t. So we have to find y of t in terms of x of t. From the figure we see that we can get y of t from x of t by expanding along time axis by a factor of 2, then by transposing the obtained signal. From this, we see that the signal y of t can be written as x of minus t divided by 2. So, this is the required relation between y of t and x of t. Now, let us consider another problem, in which the input output relation is given as shown, that is y of n is equal to x of n minus x of n minus 1. This is for n less than or equal to 0. Sine of pi by 3n multiplied by x of n minus 3. This is for n greater than 0. We have to find if the system is linear, time invariant, causal, stable, memoryless, and invertible. We see that for the given system, superposition principle is satisfied, so the system is linear. And also we see that for n less than or equal to 0, the input output relation is different from the IO relation for n greater than or equal to 0, n greater than 0. From this we can say that the system is time variant. Here we see that the output at any instant depends on current and past inputs. So the system is causal, but the output depends on past inputs. The system has memory. We can also say that for all values of n, for a bounded input, that is mod of x of n less than or equal to bx, we will get a bounded output, that is mod of y of n is less than or equal to by. From this, we see that the given system is stable. Finally, we can say that for n greater than 0, the input x of n minus 3 cannot be recovered from the output y of n using the relation x of n minus 3 is equal to y of n divided by sine of pi by 3n. This is because of the reason that sine of pi by 3n would be 0 for some values of n. So because of which x of n minus 3 would tend to infinity. So we see that the given system is not invertible because there doesn't exist a inverse system using which we cannot recover the input from the obtained output. So the system is non-invertible. So from this we see that the given system is linear, time variant, causal, stable, and it is not memoryless, and it is not invertible. Now let us consider a problem in which there are four options given. We have to pick the correct option out of the four. The option A corresponds to a system y of t is equal to sine of x of t square. Here it's given that the system is BIBO stable and memoryless. The option B corresponds to a system y of n is equal to tan inverse of x of n. It's given that the system is memoryless and time invariant. The option C corresponds to a system y of t is equal to x cube of t. Here it's given that the system is invertible and has memory. Option D corresponds to a system y of n is equal to x of n minus x of n minus 1. Here it's given that the system is linear and anti-causal. We have to pick the correct option out of the given options. If we pick the system y of t is equal to sine of x of t square, here if we see that if we give a bounded input, that is mod of x of t less than or equal to bx, where bx is finite, so this is the case for every t, then we can say that mod of x of t square is less than or equal to bx. So that implies mod of y of t is less than or equal to sine of bx. As bx is finite, sine of bx is also finite. So we can say that the system is BIPO stable. Also, we see that here the output at any instant depends on past and future inputs. So the system has memory. So from this, we see that the option A is not correct. Now let us consider the another system y of n is equal to tan inverse of x of n. Here we see that delayed version of output is equal to the output due to delayed version of inputs. So the system is time invariant. Also, we see that the output at any instant is dependent on the input at that instance. So the system is memoryless. From this, we see that option B is correct. Now let us consider the system y of t is equal to x cube of t. Here we see that the output at any instant depends on the input at that instant. So the system is memoryless. Also, we can see that the output obtained from the system can be recovered using another system, which is of IO relation x of t is equal to cube root of y of t. So we see that the system is invertible and x of t is equal to cube root of y of t is inverse system of the given system. So the option C is not correct. Now, if we consider the system y of n is equal to x of n minus x of n minus 1, we see that here the system satisfies superposition principle, so it is linear. Also, the output at any instant depends on the input at that instance or the past inputs. So the system is causal. So from this we see that the option D is also not correct. So from this we see that out of the options, the option B is correct, in which it's given that y of n is equal to tan inverse of x of n is the system which is memoryless and time invariant. Now let us consider another system y of t is equal to x of t plus 1 whole cube. We have to characterize this system based on linearity, time invariance, causality, stability, memoryless property, and invertibility. Here we see that the given system doesn't satisfy superposition principle, that is, linear combination of inputs wouldn't give linear combination of the outputs, though. So the system is non-linear. Also, here we can say that the delayed version of output, that is y of t minus t naught, is equal to x of t minus t naught plus 1 whole cube, and output due to delayed version of input, that is y dash t is equal to x of t minus t naught plus 1 whole cube. We see that these two are equal. From this, we can say that the system is time invariant. We can say that here the output y of t at every instant t depends on the input at that instance. So we see that the system is memoryless, so the system is causal as well. Now if we see that the if now sorry now we see that if the input to the system is bounded, that is mod of x of t is less than or equal to bx for every t where bx is finite, we see that mod of y of t is equal to mod of x of t plus 1 whole cube. As the input x of t is bounded, we can show that the output y of t is also bounded, that is mod of y of t is less than or equal to by, where by is finite. From this we see that the system is stable in BIBO sense. Now finally we can see that for any in suppose for any given input x of t, if the output of the system is y of t, we see that the input x of t can be recovered from the output using the relation x of t is equal to cube root of y of t minus 1. So from this we see that the system is invertible, or x of t is equal to cube root of y of t minus 1 is the inverse system of given system. From this we see that the given system is nonlinear, time invariant, memoryless, causal, PIB was stable, and is invertible. As per the current problem, there are four options given where each option corresponds to a discrete time system. We have to find if each of these discrete time systems is invertible or which of the discrete time systems is invertible. The option A corresponds to y of n is equal to sine of 2xn, and the option B corresponds to y of n is equal to x square of n plus x of n, and option C corresponds to y of n is equal to 2 into x of n plus 5. Option D corresponds to y of n is equal to x cube of n plus x power 4 of n. We know that a particular system with the IO relation y of n is equal to transformation of x of n is invertible if we are able to find a relation T inverse such that the input x of n can be recovered from the output y of n using the relation x of n is equal to T inverse of y of n. Now we see that if we pick the system in option A, the inverse system that we can get is x of n is equal to half sine inverse of y of n. Here we see that the output in the input x of n cannot be recovered exactly for all values of y of n due to the many to one relation of sine inverse function. From this we say that the given system is non-invertible. And if we see the system in B, y of n is equal to x square of n plus x of n. Here we see that due to x square, there is a loss in information. So from this, we say that the given system is non-invertible. Now, if we pick the system in option C, here y of n is equal to 2 into x of n plus 5. Now, from this, we can say that the input can be recovered from the output using the relation x of n is equal to y of n minus 5 divided by 2. So the system in option C is invertible and x of n is equal to y of n minus 5 divided by 2 is the inverse system of the given system. Similarly, the system in D is not invertible due to the term x power 4n, hence there is a loss of sign information. So from this we see that the system in option C, that is y of n is equal to 2 times x of n plus 5, is invertible. Now let us consider another problem in which there is a signal x of n which is given as shown, that is x of n's value is 1 at n is equal to 0 and its value is half at n is equal to 1 and minus 1. It is given that there is a derived version of x of n that is given as y of n is equal to minus x of n by 3 if n is a multiple of 3, it is 0 otherwise. Now we have to find y of n in terms of x of n. So from this we can see that y of minus 6 is equal to minus x of minus 2 which is equal to 0. Similarly, y of minus 5 is equal to y of minus 4 is equal to 0 because minus 5 and minus 4 are non-multiples of 0. So we can see that y of minus 3 is equal to minus x of minus 1. So this is equal to minus half. So y of minus 2 is equal to y of minus 1 is equal to y of 1 is equal to y of 2 is equal to 0 because all these dimensions are non-multiples of 3. And so from this y of 0 is equal to x of 0 is equal to minus x of 0. So this is equal to minus 1. Similarly, y of 3 is equal to minus x of 1 is equal to minus half. From this, we can say that the y of n can be plotted as shown, where y of n is non-zero at the instant n equal to 0, 3 and minus 3, and it is 0 at all other instants. So at instant n is equal to 0, y of n is minus 1. At the instant n is equal to minus 3 and 3, its value is minus half. And at remaining all instants, that is n equal to 1, 2, minus 1, minus 2, minus 4, minus 5, 4, 5, the value is 0. So all those are the instants which correspond to the regions marked. So at all these points, the value of y of n 0. So from the given x of n and the given relation between x of n and y of n, we can obtain the y of n as shown in the figure. So this is the required answer. There is a discrete time signal given, that is x of n is equal to 3 comma 1 plus 2j comma j. Here the value 1 plus 2j corresponds to the instant n is equal to 0. We have to find the conjugate skew symmetric part of the signal. Here the signal is imaginary, so the conjugate symmetric part of the signal is given as x of n minus x star of minus n divided by 2. From the given x of n, we can find x star of n, that is conjugate of x of n as 3 comma 1 minus 2j comma j, and from this x star of minus n can be written as j comma 1 minus 2j comma 3. This is obtained by transposing the signal x star of n. Now from this we can write the conjugate symmetric part of the signal as xo of n is equal to half multiplied by 3 comma 1 plus 2j comma j minus j comma 1 minus 2j comma 3. So which upon simplification can be written as 3 minus j by 2, 2j, then minus 3 plus j divided by 2. So and the center is around, and the center is at the point, sorry, and the value in 2j corresponds to the instant n is equal to 0. So the obtained signal is conjugate skew symmetric part of x of n. Now let us consider another signal. Sorry, now let us consider another problem. There are four systems given in the options A, B, C, and D. The systems are y of t is equal to x of t divided by 2, y of n is equal to x square of n plus 1, y of n is equal to x square of n minus 3, y of t is equal to x of t plus 2 divided by 3. We have to find which of these systems are causal and non-invertible. If we consider the system in option A, that is y of t is equal to x of t divided by 2, we see that the output at any instant depends on the input at that instant. So from this the system is causal. Also the system is invertible, and the inverse system can be written as x of t is equal to 2y of t, because here the input can be recovered from the output completely. Now let us consider the system in B, where y of n is equal to x square of n plus 1. Here we see that the output at any instant depends on future input only. From this we see that the system is anti-causal, hence non-causal. Also due to the square, we see that the input cannot be recovered completely from the output y of n. So we see that the system is non-invertible. Now let us consider the system in option C, that is y of n is equal to x square of n minus 3. Here we see that the output depends on past input, so the system is causal. Also due to square term, we can say that the system is non-invertible. Now if we consider the system in option D, y of t is equal to x of t plus 2 divided by 3. Here the output at any instant depends on future input only. So the system is anti-causal and hence non-causal. Also the system is invertible. From this we see that the system in option C, that is y of n is equal to x square of n minus 3, is causal and non-invertible as required. Hence, C is the correct option. Now let us consider a signal f of t is equal to 10 into cos of 10 pi t multiplied by sine square of 20 pi t. We have to find the time period of the signal f of t. So we can simplify f of t as 10 times cos 10 pi t multiplied by 1 minus cos 40 pi t divided by 2. This on simplification can be written as 10, sorry, can be written as 5 cos 10 pi t minus 5 by 2 multiplied by cos of 50 pi t plus cos of 30 pi t. From this, we can see that the signal f of t is sum of three signals, each of angular frequencies 10 pi radians per second, 50 pi radians per second, and 30 pi radians per second. From this, we can find the time period of the signal as 2 pi by omega, hence 1 by 5 second, 1 by 25 second, and 1 by 15 second. From this, we see that the time period of the signal f of t is equal to t is equal to LCM of 1 by 5, comma 1 by 25, comma 1 by 15. From this, we see that the time period of the given signal is equal to LCM of zero point 0.2, zero point 0.2, 0.04, and 0.0667. So this can finally be written as zero point 0.6 second, because zero point 0.2 into 3 is 0.6, 0.04 into 15 is zero point 0.6, and 0.0667 into 20 is 0.0667 into 8 is 7 into um, sorry, so this is equal to LCM of these values. From the above obtained individual time periods, we can see that overall time period of the signal is t is equal to LCM of 1 by 5, comma 1 by 25, comma 1 by 15, which is equal to zero point 0.2 second. So zero point 0.2 second is the time period of the given signal f of t. Now let us consider another problem. In this, there are four discrete time signals given in the options A, B, C, and D. We have to find which of these signals are periodic. The option A corresponds to sine pi by 3n plus sine 2 pi by 3n. Option B corresponds to sine n plus sine 3n. Option C corresponds to sine n plus sine of root 3n. Option D corresponds to sine pi n multiplied by u of n. We know that given a signal sine of an is periodic if sine of an a capital N plus sine of an is equal to sine an. So for that this should be equal to sine of 2 pi k plus an. From this we can say that a into n should be equal to 2 pi k where k belongs to z. So n should be so the given signal would be periodic if n is equal to 2 pi k divided by a where k belongs to z is an integer. Further to happen, a should be a multiple of pi. So then only the given signal sign of an would be periodic. From this we can say that the signal in option A, that is sine of pi by 3n plus sine of 2 pi by 3n, is periodic because the individual signals sine pi by 3n, sine 2 pi by 3n are periodic. So the sum of signals is also periodic. Now let us consider the system in signal in option B, which is sine n plus sine 3n. Here we see that the individual signals are non-periodic. From this we see that the sum is also non-periodic. Similarly, the signal sine n plus sine of root 3n is non-periodic. Also, the signal sine of pi n multiplied by u of n is non-periodic because the signal is present only for n greater than or equal to 0. From this we see that only the signal in option A is periodic. Now let us consider another signal x of n is equal to 1 by 2 multiplied by cos 3 pi by 7n plus 3 into sine of pi by n plus theta. Sorry, 3 into sine of pi by 4 n plus theta. Now we have to find the time period, the period of the overall signal n. For this, we have to find the individual time periods, that is, the period of the signal cos 3 pi by 7n and sine of pi by 4n plus theta. We know that the signal cos 3 pi by 7n is periodic with a period n1 is equal to 14 and the signal sine of pi by 4n plus theta is periodic with a period n2 is equal to 8. From this we can say that the sum of the signals is periodic with a period of n is equal to LCM of n1 comma n2, so which is equal to 56. From this we see that the given signal x of n is periodic with a period of 56. Now let us consider another signal which is given as x of n is equal to 6 comma 2j comma 4 comma minus 4j comma 10, where the value 4 corresponds to the instant n is equal to 0. Now we have to find the conjugate symmetric part of the signal xe of n. We know that the conjugate symmetric part of the signal xe of n is given as half multiplied by x of n plus x star of minus n. Upon substitution, this can be written as half multiplied by 6 comma 2j comma 4 comma minus 4j comma 10 plus 10 comma 4j comma 4 comma minus 2j comma 6. This upon simplification becomes 8 comma 3j comma 4 comma minus 3j comma 8, where the value 4 corresponds to the instant n is equal to 0. So by using the given formula half x of n plus x star of minus n, we obtained the conjugate symmetric part of the signal as 8 comma 3j comma 4 comma minus 3j comma 8, where the value 4 corresponds to the instant n is equal to 0. Now let us consider another problem as per which there are four systems given in the options A, B, C and D. The option A corresponds to the system y of n is equal to log of mod of x of n. The option B corresponds to the system y of t is equal to integral 0 to t x of tau d tau. Option C corresponds to the system y of n is equal to x square of n minus x cube of n. Option D corresponds to the system y of t is equal to e power x of 2t. We have to find which of these systems is nonlinear and time variant. We see that from the option A, the system doesn't satisfy superposition principle, so the system is nonlinear. Also, we see that the delayed version of output is equal to the output due to delayed version of input, so the system is time invariant. Similarly, we see that the system in option B is linear as it satisfies superposition principle, and also it is time invariant. Now we see that the system in option C satisfies superposition principle, so it is linear. Also the output due to delayed version of input is equal to delayed version of output, so this system is time invariant. Finally, we see that the system in option D is non-linear as it doesn't satisfy superposition principle. Also, due to the factor 2 on the time, the output due to delayed version of input is not equal to delayed version of output. So the system is time variant. From this, we see that the required system, which should be non-linear and time variant, is the system in option D, which is y of t is equal to e power x of 2t. Now, let us consider another problem as per which there is a signal x of t is equal to sine of a square t multiplied by cos of t by b square given, sorry, added by. Now, we have to find the condition for which the signal x of t would be periodic. We know that the signal sine of a square t is at an angular frequency of omega 1 is equal to a square, and the signal cos of t by b square is at an angular frequency of 1 by b square. We know that the individual signals are periodic. So for the signal x of t to be periodic, omega 1 by omega 2 should be rational. That is, a square divided by 1 by b square should be rational. That implies a square b square should be rational. So for the given signal to be periodic, a square b square should be rational. Now let us consider another problem as per which there are four systems given in the options A, B, C and D. The systems given are the system given in A is y of t is equal to sine of x of t plus 3, y of t is equal to sine of integral minus infinity to t x of tau d tau, y of t is equal to cos of x of t minus 2, and none of these. We have to find out of the four options given the option that corresponds to causality and not stable case. If we see the system in option A, we see that the system The output at any instant depends on future input. So the system is non-causal or anti-causal. Also, for a bounded input, the output is bounded. So the system is stable. Similarly, if we pick the system in option B, we see that for a bounded input, the system would give a bounded output. So the system is stable. Also, the system also the output at any instant depends on past inputs only. So the system is causal. Similarly, if we pick the system in option C, we see that for a bounded input, the output is bounded. From this, we see that the system is stable. Also, the output at any instant depends on past inputs only. So the system is causal. From this, actually, our intention is to find a causal and unstable system, but the options A, B, and C don't correspond to the same. So the correct option is B, which means none of these, as we are not able to find a causal and unstable system.